All right, so let's talk about this. This is the Safe Sleep bash script. It is a part of the GitHub Actions Runner repository on GitHub. So this went a little bit viral maybe like 2 weeks ago, and I've had a couple people ask me like, Dave, when are you going to talk about it? It's a bash script. It's right up your alley. And you're right. It is right up my alley. I didn't want to jump on it right away because it is kind of breaking. It's kind of breaking news. I mean, it's kind of viral, and I don't want to jump on that when people are kind of scrambling to figure things out. Some people are throwing out some very passionate words around it. So I wanted to wait for all that to sort of die down. I wanted to wait for a lot of this to kind of be figured out and solved and fixed so we can kind of talk about it like a post-mortem sort of what happened. I say that to say I don't work at GitHub. I don't work on this code base. I'm not super familiar with it. I'm not the target audience of this code base. I'm just going to talk about the bash code specifically because that's in my wheelhouse. That's what I know. I released a whole 7-hour course on bash that you can go check out for free on my channel. Doesn't cost you anything. And yeah, that's it. That's the only plug for this video. Let's jump in. All right, so to get started, there are a couple different issues and a couple different pull requests that really go over this. This is sort of the main one. There's a lot going on here. It talks about the safesleep.sh bash script, and there's a lot of stuff going on here. There's a lot of choice words. It gets very passionate. We're not going to go through this. We're not going to litigate this. This has already been figured out. This is not our place. I don't want to dive into the specifics or what happened here. I just want to talk about the code as it was and the code as it is now. I just kind of want to review what there is, how it works, and some of the intricacies of it, and some of the bugs that were present with it. So here it is. Here's the code. Take a look at this. It's a simple bash script. And all it does is define seconds to 0, and then it has this little while loop that runs colon. That's a little bit confusing. I'm going to take this, I'm going to pull it down on my terminal, and let's actually have this script on our machine. Okay, here we go. I got the script down here. We have safesleep.sh. We open it up, and it's exactly that. So let's study this before we run it, okay? We have a shebang at the top, and it's bin bash. Now, I don't know what the system this is supposed to run on is. I don't know how these GitHub actions are executed. I'm going to assume this is some sort of bash shell. This isn't intended to be run by like a Born shell or a ZSH shell. I have no idea if that's the case or not, but that's the assumption based on the shebang here. I don't know what their environment looks like. It's not really relevant. I can just sort of look at the code and figure out this. We declare a variable called seconds. We set it equal to 0, and then we check while seconds with a $sign in front of it, so it will expand to the value of seconds, while seconds is not equal to $1. There's a lot going on here. We have the double square bracket notation. This is a bashism. You might find this in other shells. This is not going to be in a POSIX shell or a Born shell script. This has to be bash or some other shell that supports it. And then we have $seconds not equal to $1. $1 is an argument, so we're expecting the user to give us some sort of argument. And then what do? We do colon in a loop. Okay, so what is colon? We can do help on colon, and we can see it's built into bash. It's the null command. It has no effect, doesn't do anything. If you've ever seen like a fork bomb, I'm not going to run it, but if you ever see a fork bomb, we redefine a function called colon. Colon's a valid name. Colon does exist on bash. I run it, it does nothing, and it exits with success. So what's happening here is we're saying while the variable seconds is not equal to whatever the user gave us as the first argument, we do nothing. And we keep checking this until this condition is met. So how would that ever work? How would seconds ever get incremented, right? That seems kind of confusing. Well, seconds is a special variable to bash. We can pull up the bash man page using man bash. We can search it for seconds, and we're going to get a lot of stuff. There's like new things, bash monoseconds, there's epoch seconds. Here we go. Each time this parameter is referenced, it expands to the number of seconds since the shell invocation. So this will tell you the number of seconds the shell has been running. If a value is assigned to seconds, the value returned upon subsequent references is the number of seconds since the assignment plus the value assigned. So that's what's happening here. It's being assigned to 0, so that will count up from 0 because we've set it to 0. So it's however many seconds since it was assigned to 0. Cool, that's awesome. The number of seconds at shell invocation and the current time are always determined by querying the system clock at 1 second resolution. That's important too. So what does that mean? Let's go ahead and echo seconds here, and we can see that my shell's been running for 808 seconds. If I do it again, 811 seconds. If I do it again, 813. According to that man page, we can set it to 5, and then we rerun it. It will be 5 plus the number of seconds since it's been set. So that's pretty cool. So if you remember the script, let's go ahead and look at the safe sleep script. That says seconds equals 0. So if we set seconds to 0, and then we immediately look at it, we can see it's already up to 2. We already missed 2 seconds there. We missed at most 2 seconds, at least 1 second, plus a little bit more. What I mean by that is the man page said 1 second resolution. So if I set it to 0 and the clock is just about to turn to the next second, it will become 1 almost immediately. So already I could see a problem here. If I give the sleep command, let's say the number 5, I want to call safe sleep with the argument 5 here. Seconds get set to 0. It will count up to 5, but it might get to 5 in 5 seconds, or it might get there in 4.01 seconds, or somewhere in between. So most likely, on average, this thing rates to sleep about 4.5 seconds if I give it the argument 5. Something to keep in mind. There was one more thing in the bash man page. You'll see this a lot with bash built-in variables. It is super, you just see it everywhere. If seconds is unset, it loses its special properties, even if it's subsequently reset. So this is not relevant to the safe sleep script. That's hard to say fast, but this is important to know. If I were to run something like unset seconds, and if I were to run this and then subsequently reset it, it wouldn't keep counting up. It would lose that special property. I'm not going to do that, but I'm just letting you know that's how that works. So what's happening here? Let's look at the safe sleep script, and we can see that it counts up and it runs this colon command. This colon command returned really fast. So this loop executes very, very, very fast. All right. I can prove this. Instead of doing colon, let's say echo, oh, look, it uses 4 spaces and I use tabs. That's so fun. Let's say echo, it has been seconds. Let's comment this out, even though it doesn't do anything. And let's go ahead, let's look at that script and let's run it. Let's try and run it for 5 seconds and we'll see what happens. What's called safe sleep 5. As you can see, there's a lot of output there. So if I scroll, I mean, look at the scroll bar. So it's extraordinarily busy while it waits. In fact, there's a name for this style of sleeping, and it's called busy wait, or this is busy wait time. The process is busy, and it's happening in the user space. I'll explain what that means. So let's get rid of this. Let's go back to what we have here. So we have this colon operation. So the way this works is I can call safe sleep with 5, and it will sleep for 5 seconds. Now, like I told you before, it'll technically sleep somewhere between 4 and 5 seconds. On average, I think we're going to hit 4.5. There we go. Look at this. We hit 4.849. That's really cool. If I ran it again, there's a chance it could be lower, it could be higher. More likely it's going to be lower, just statistically. Oh, look at this one. This one only ran for, wow, just barely over 4 seconds, even though we wanted 5 seconds. I got really lucky with that. That wasn't edited or anything. I just got really lucky with that. So here's something interesting. Notice where it's spending its time. If you've never seen the output at time, the time command is built into bash, though you probably will have it on your machine. The output might look slightly different. There's real time, there's user time, and there's system time. So the real time is the wall time. This is how long it took on a wall clock. If you held up a clock here and 4.8 seconds went by, that is how long it took for this to run. It's a stopwatch, effectively. There's user time and there's system time. And you might look at this and be like, oh yeah, they kind of add up roughly. Be careful with that. But yeah, they kind of do here. User space is how much is in your process, how much your process is doing. This is going to be CPU bound work. This is going to be mathematical calculations. This is going to be heavy string manipulation, things that your program does inside its own little world. System time, by contrast, is how much time is spent in the system or the operating system or the kernel, whatever you want to call it. This is time spent in the kernel, but on behalf of your process. So your process has asked the kernel to do something. This would typically be I/O, input, output, writing to a network device, writing to a disk. Anytime you ask your system to do something like through, let's say, system calls, so, open, read, any sort of, a lot of file system manipulation stuff, a lot of networking stuff. There's other things, but basically that's anytime the system or the kernel or the operating system is doing work on behalf of your process. That's how much time is here. So when the system is actively doing work, it's counting up how much time. And when the user space is doing work, it's counting up how much time. And at the end of it, it says that it spent a cumulative 4.7 seconds here and a cumulative 0.05 seconds here. So this is not great. I'm just going to tell you right now, this is not great. The reason it's not great is because you shouldn't really be doing this much work in user space. That's utilization. That's if I were to look up my process manager, I would see that bash is actually lighting up that CPU. It's actually doing a lot of work. Even though the work is kind of meaningless, it's doing work. Typically, when you sleep in a program, you don't want to do it in user space like this. You want to alert the kernel, hey, I want to sleep for 5 seconds. So instead, just park me for 5 seconds. Just freeze me for 5 seconds. Then in 5 seconds, unlock me, unfreeze me, wake me up. The kernel's extraordinarily good at doing this. It has a whole bunch of timers it manages under the hood. Obviously, different operating systems are going to differ in their implementation, but from a conceptual level, the kernel manages timers. It's very good at it. That's what it does. So as a user program, I can just say, hey, freeze me and then wake me up when this happens. There's alarm mechanisms, like a SIG alarm you could set. There's a lot of, if you do like programming with asynchronous operations and you want to read from something, the kernel manages, I can actually wait for this data to become ready and the program doesn't need to run until the data is ready. There's certain things you can do like that. Really cool stuff. And the important part is that it's efficient. The kernel is very efficient doing that because it doesn't have to constantly check, has this condition been met? I'm not spin locking on this specific thing to be met. No, I can just kind of go to sleep until I'm told to wake back up. So let me show what that looks like, because if I were to take this safe sleep program and instead of doing all this stuff, let's just replace it with sleep $1, and then we'll put an exit here. Notice that exit call, so we won't run any of the code below it. We're just going to call sleep and we're just going to exit. I'll put the source code up here so you can see it. If we run this and then we give it 5 and we put a time in front of it, let's see what happens now. Look at this, okay? We slept for at least 5 seconds, which makes sense because there's a little bit of startup time to actually run the bash script and do whatever's necessary. There's not much that happens here, but this sleep binary is going to run for 5 seconds and everything else is on top of it. So when you sleep for 5, you're going to sleep for at least 5 seconds, which is in stark contrast to the original safe sleep script that could go anywhere between, 4 to 5 seconds. Here's the thing. Look at how much time was spent in user space, but look at how much time was spent in system space. There's like nothing. Like they're basically doing nothing. This was how much time it basically took to parse this string and call sleep. That's pretty much what was happening in these, 3, milliseconds? And in these 6 milliseconds, that's how much time it was to tell the kernel, like, hey, put me to sleep. And then the kernel would be like, hey, time to wake back up. That's it. So if you're expecting this to be like 5 seconds of system time, that's not how time is monitored. I would have to get the kernel to spin lock for 5 seconds. There may be ways that I could do that, but I'm not really going to try and do that. There's no reason you would want to do that. So this is something important, like I mentioned before. User and system time don't need to add up to the real time. The wall time, how much time it actually took on the clock, doesn't really change here. If I were to give it like something else, if I were to say, let's just do this for 2 seconds instead, I would expect the user time and the system time to be relatively the same. They're really close to each other. That's because it takes the same amount of time to parse this string, and it takes the same amount of time to tell the kernel, hey, put me to sleep and wake me back up. Whether that sleep lasts for 2 seconds or 10 seconds, that's timers. The kernel's already managing all that stuff. So that's something interesting. So it's interesting that the sleep happens in user space. Now, are there valid reasons for that? Well, yes, on certain systems, of course there are. There are valid reasons to do this. Maybe if you're on like an embedded system that doesn't have like a kernel that manages timers for you. I've written code for the Nintendo 64 where sometimes you have to spin lock in user space because that's like all you can do. That's your way of sleeping, to wait for like the next frame or something. There may be other ways, but like what I'm saying is I can think of valid reasons for this. But if I'm looking at a bash script, I'm thinking, oh boy, we're already so high level with bash. Why are we doing it in the user space? Again, I'm not diving into the specifics of the actual repository where this comes from. I'm not interested in that. I just want to look at this code specifically and try to understand it in isolation. So let's go back to our safe sleep here and let's talk about something else, because there is a bug here. Now this bug was fixed in subsequent versions of this. So that was part of that whole PR issue thing. The bug is this. We say while seconds is not equal to $1. Well, can you think of a problem? Remember when I ran it before and it showed how long it was sleeping? And like, look, when I scroll through it, see there's a bunch of 4s, a bunch of 3s, a bunch of 2s, and a bunch of 1s. What if the system was really busy? Like, I'm recording this on a really beefy computer that has a lot of spare CPU cycles. So it can print a lot of times. It can check multiple times per second. But what if the machine was really busy? What if this check only ran once every 2 seconds? Let's imagine it that way. Let's say we set seconds equal to 0 and we're checking to see if seconds is equal to 5, right? We give it the argument 5. Well, what if seconds is 0 and then we don't check again for 2 seconds? Okay, now seconds is the number 2. Well, 2 is not equal to 5, so we keep going. Then seconds is equal to 4. 4 is not equal to 5, so we keep going. Then seconds is equal to 6. 6 is not equal to 5, so we keep going. You see the problem there? So this is just sort of like unbounded. We're only checking for a specific target, and we are at the mercy of the scheduler of the operating system that is running the script. So to fix this, you'd probably want some sort of like less than or equal to check. So you could do this notation. You could do like less than equal to this. And if you run this, this will work kind of how you expect. So if we run that, then it runs, and you will see that when it hits the point, look at that. So it stopped at 2.78. Yeah, I think the less than equal, maybe you just want less than, because if you do the less than equal, it's going to be above your target. If you do the less than, then it will be below the target. That was just a simple off by 1 error. But as you can see, what I'm trying to stress is the, binding it to some sort of maximum value. We never let the value get above 2. Say we get thrown off the schedule and the computer is completely running so slow for like a minute. When we come back, we just stopped running. Yeah, we ended up sleeping for a minute. That's not great, but we're done because it was over 2 seconds. So that's kind of the way to look at that. All right, so before we look at the next iteration of this script, I want to show something cool to kind of stress a different point. I'm going to take this and I'm going to put this in a function, okay? We'll call this my sleeper. That's the name of the function. Open the curly braces, go down here, tab that over. Let's make it tabs now because I like tabs instead of 4 spaces. You guys can yell at me in the comments, that's fine. So look at this, we have my sleeper where it does this and it just does that. That's all it does there. So if we do my sleeper and let's say 5, then it will do exactly what we've been doing with the argument 5. There's nothing different here. We've just moved it into a function. Why have we moved it into a function? Because now we can put it in the background. I can background this job, and then I can call wait, which will tell bash to wait for all background jobs to finish before we move on. So we just ran the same code the hard way. That's all we've done. We haven't actually made any changes here. It's still going to work exactly the same. We just don't give it an argument now. The argument is implicitly 5 because it's set in the script. So we run this, it sleeps for 5 seconds. That's all well and good. Let's go ahead and let's duplicate that line, okay? So now we have 2 sleepers. They're both gonna run for up to 5 seconds, but we have 2 of them. So why am I stressing this point? Let's take a look at this. Let's go ahead and time this and see what we get after 5 seconds. Look at this. Okay, look at the real time here, 4.7, so it was up to 5 seconds, but look how much time was spent in user space. And I'm gonna be honest, I'm very surprised to see this much spent in system time, but here's the thing. This is almost double that, right? If you add these together, you get roughly 8, and this thing ran for roughly 4 to 5 seconds. So it's double because, yeah, it's double. It spent more time in the user space because this forked. This forked and exec. Let me actually pull up this one. There you go, because it calls it twice. So it forked and exec this twice. So 2 of these are running, 2 of these are spin locking, 2 of these are in busy wait, and they are on individual CPUs. Yeah, so when you have multiple simultaneous things running, you can see that user time might be higher than the wall time because it was like 2 individual things running, one for 3.5 and 1.3.5 or 3.6, 3.6, whatever. They add up to 7.2. That's what happens here. And of course, we can do this more than once. We can just take this, copy and paste it, do it 4 times, right? So if we run it 4 times and then we tell it to sleep for up to 5 seconds, you would expect it to be roughly 4 times 2, 5 times 2, somewhere between that. So look at this, we get 14.238. Like I said, 4 times 2 is gonna be like 16. It's actually a little bit less than that. So yeah, a little bit surprising to me, but hey, look at this. That's kind of interesting here. So again, when it's in user space like this, it is burning the CPU. It is making the CPU do work. It is actually taking some processing time to do this. If I were to put this on, let's say like 20 cores, and I were to make it sleep for 60 seconds, my fans would probably start kicking out on my machine. So be mindful of that, be wary of that. Let's talk about the next iteration of the script though. Okay, so here it is here. It's the same exact file, but I am in the main branch at the time of this recording, which is Thursday, December 18th. So it may have changed since then, but this is what it looks like now. I'm gonna copy this over my terminal. Okay, so I've copied it over. It's the same name, but if we look at the script, you can see there's a lot more going on with it. Let's talk about it before we even run anything, okay? Hey, look, there's some comments here. That's very nice. Try to use sleep if available. So there is a command. It's called sleep. You run sleep like this, you give it a number, and it sleeps for that long. We've already used this before. It's a very efficient way to sleep. I don't know how I pulled up that. Time sleep 3. It's a very efficient way to sleep because it just sort of instructs the kernel, hey, shut us down and wake us back up. As you can see, almost no user time, almost no system time. So that's really good. That's what we want here. So we check. There's a couple things going on here. We're using single square bracket notations. Interesting because the shebang says bash, but we're using single square brackets. But I already know if you peek below here, we're using double square brackets. So it's a weird mixture of syntax, not a problem. I'm just interested into why that's the case. We can see if this means if it's executable. So this checks, this -x checks, is this file executable? And instead of a file, we're giving it a command using command substitution here. So this will resolve to a file. So let me show what that looks like. We can do command-v sleep. We run this and we get the path to the executable sleep. This will be the one that my shell will actually execute. The nice thing about this is POSIX specified, so you can expect this to be here on like a Unix or Unix-like operating system. So a little bit of a light mode jump scare here, but as you can see, I have the POSIX specification pulled up. Which one is this? 2024. So you can see there is a command, named command, and it will have the -v, which will write a string to standard out that indicates the path name. There are some specifics about it, but basically you can expect that to be here. In our case, it does happen to be built in to bash. So bash has this command built in, but you can expect it to exist on the system, which is super nice. So if I were to run a type -a of command, you can see it's a shell built in, but it also exists on my system. It's going to be there. I'm on a Mac, and Mac is like a Unix-like operating system. It has most of the POSIX tools. I don't know if it's fully POSIX compliant, but I can do this. I can say Command-V and then give it sleep like this, and it works exactly the same because there's a very strict rule on how it's supposed to work. So we have this, and then we're checking -X on it. So if I do -X bin sleep, that's effectively what's being ran here. We can see that we exit with success. That means that program exists and has the executable bit turned on. Now, it's a little bit surprising at first that you would check it this specifically. It's a little bit pedantic here. It's not wrong. It's just that I would usually consider Command-V sleep to be enough. However, it will resolve commands that aren't executable. So technically Command-V sleep could work. And then when you go to call sleep down here, it fails because it's not executable. So this check is fine. This check is totally valid, and it's definitely checking, does this program exist and is it executable? If it is, then we execute it with the argument that the user gave us. Get back to that one because that one was a little bit important here. The next thing we do is we check, does the user have the ping command? If so, we run ping like this. Now, I recognize this. I recognize this from like 20 years ago, having to admin Windows systems. That's not a deep part of my lore. I did it just kind of like ad hoc, and I wasn't very good at it, okay? But I've seen this before. This was a hack to sleep. So what you do, it's actually pretty clever, because by default, ping works by pinging something every second, and -C tells it how many times to ping something. So let's ping something that's guaranteed to work, 127.0.0.1. That's always points to our machine. That's a local host. Ping something that's guaranteed to work, the argument 1 + 1 times, n + 1 times. So if I want to sleep for 5 seconds, I have to ping it 6 times. Why 6 times? Because the first one is instant, and then it sleeps 1 second between pings. So if you want to sleep for 5 seconds, you need to ping 6 times because those 5 sleeps will be sandwiched between the 6 times. This looks like this in practice. If I were to run ping 127.0.0.1, it'll run forever until I Control-C. Now, if I were to put a ping-C4 here, and let's go ahead and time this command, it will run for, what do you think? That's right, 3 seconds, because we gave it n + 1. If n is 3, then we give it count of 4 here, it'll run for 3 seconds. So it's a clever hack. Things get really bad if there's timeouts. If ping for some reason has a timeout pinging localhost, I don't know how that could ever happen, but then we could get some weird situation where we sleep for a lot longer. But this is why it's important to define your programs. Like, you know, I didn't make this program. I don't know what safe sleep is supposed to do. Obviously, I can look at its name and infer. I don't know if I call safe sleep a 5, do I expect it to sleep for at most 5 seconds or at least 5 seconds? Because if it sleeps for at least 5 seconds and ping hangs, like, hey, yeah, it slept for at least 5 seconds. It might have slept for 5 minutes, but it slept for at least 5 seconds, right? I would want my sleep command to go a little bit longer than a little bit shorter, but that depends on you. That depends on what this command is for. A command is fit for a purpose. It depends on the purpose. It depends on how it's documented. I don't see any documentation here. I'm not faulting this. This is not my project. I am not the target audience of this project. Again, we are just talking about the code. I just want to stress that point. So now we go down here and we try to use read-t if we are in bash. Now I know about this because in bash, we have the read built in, and read built in is really cool because it has a lot of arguments here, but look at this. It has the -t argument of timeout. So it'll cause it to hang for that amount of seconds before it gives up. So you can give it a -t of 5. It'll try to read from a file, and after 5 seconds, it'll just give up if no data was found. So what we do here is we check if bash version is set. That's how we're determining if we're in bash. Fine. I don't have a problem with that. There might be some issues. Maybe someone could, export this as an environmental variable. I don't know what people's environments look like. I'm not going to fault them. I think this is a fine way of doing it, really. Like, it's not the end of the world. I'm a little bit surprised. The shebang says bin bash, so I don't know how this is being executed where it couldn't be bash, but maybe their system runs it through different runners. Maybe it's a bash or a dash or a Bourne shell or ZSH. I don't know. The next thing we do is in this nested if statement, we check is read available as a command. This is surprising to me. I would expect read to be there, but hey, nothing wrong here. It's just being a little overly productive. We're throwing everything out to dev null. Again, if we already determined we're in bash, we could probably just do this syntax, which will throw everything out to dev null. But using this old syntax probably makes it work on really, really old versions of bash. Again, without knowing what version of bash they're targeting, I don't know how explicit we need to be. I don't know how defensive we need to be when we program. So then we have 3 of these blocks of code that are largely the same. The only difference is this number, 0, 1, and 2. Now they say what they are up here, standard in, standard out, and standard error. Now, that's what's going on here. We're checking if standard input is a terminal, meaning it's a TTY. It's not being read in from a file. It's not being like, piped in from dev null or piped in from a command. No, if it exists as a TTY, as a terminal that someone's sitting in front of, or, some sort of pseudo terminal, then we will call read on it. We'll read from that file descriptor. That's what U is, the number file descriptor. And we'll read with a timeout of whatever the user gave us. And then we'll exit 1. I don't know why this is here. This is a short circuit notation. So we're basically saying do that logically ORed with the null command. So basically if read fails for whatever reason, we run this colon command. If read succeeds, we never run it. But if read fails, we run colon, which does nothing. It resets our exit code. And then we have a semicolon here, which is completely redundant. In bash, you don't need semicolons. So that's doing nothing, actually. We get rid of that. And then this just changes the exit code of the read command, but we never look at the exit code of the read command. We just exit explicitly here. So again, this does nothing unless this was being invoked in some sort of unless some runner of the script was doing bash -e on it, which would set error exit, then we could have a problem. I don't know how it's being executed by their commands. Again, this isn't my project, but if we're just looking at this as a bash script in isolation, you just get rid of these. So all we're saying is if standard is a terminal, then we will use that terminal to invoke a timeout on because we don't expect to be able to read anything. If standard out is available, then we'll do the same thing there. If standard error is available, then we'll do the same thing there. You can totally do this. Fall back to busy wait. So as you can see, this is the original code with the less than notation here. This is the original code that was there. So we're basically saying try to do these more advanced ways of sleeping. If we fail, fall back to this one. This is fine. This works. This is what's currently in main. I don't really have a specific problem with this. When I look at this, I don't immediately I should clarify what I mean. When I look at this, I don't see any immediate security vulnerabilities or things where I'm worried about that. So if I did, I wouldn't be talking about this video. I would be alerting them privately. That's the right thing to do. I will tell you that I haven't seen anything. There's no security thing that I've noticed here. There's no problems. There's no exploits. There's nothing I would want to necessarily report to them. Now I could clean this code up, but let's not even talk about it. Let's just run it. Let's just see what happens. Because if we run safe sleep with, let's say 5, and we give it a time, what should happen if we look at the code, we can actually guess what's going to happen. We should have a really good sleep. And we do have a really good sleep. Look at this. Perfect REM cycle. We're very well rested. We slept for 5.3 seconds. We have almost no user time and almost no system time. That's great. That was an efficient sleep. That is fantastic. That's what we want. If we were to bash -exit, bash -x, this will give us debug output. We'll be able to see exactly what version of sleep it used. It's probably going to use the sleep binary, and it does. It checks for the sleep binary, and then it calls sleep 5, and then it should call exit 0, and it should be done. There you go. That's perfect. That's all it did. It didn't have to do anything else because this binary existed on our system, and we can use it. There are little things I'm a little bit worried about with this code, so I'm going to go through and give it a little bit of a review and a little bit of a critique, just places where I can see an issue. Again, I think this is fine for its purposes, and I don't have any intention of changing it, but let's go ahead and imagine if this were like my script, what would I do with this? So here's what I would do first. Look at how many times $1 is referenced. If I search for $1, it's referenced here a lot. That's the argument the user gives us. What if we don't give an argument? What if we just call safe sleep? Well, the error message came from the sleep binary. So we're relying on these tools to give us the error message. If the sleep binary was not there, then we're relying on ping to give us an error message, right? So let's imagine a world where the sleep binary is not here, okay? Let's say instead of command-v sleep, we're looking for fake sleep. That doesn't exist. So we are going to fail the if statement, and we're going to carry on to the ping solution. So we're going to run the ping command. What's going to happen when I don't give it an argument? It returns immediately. It returns immediately and exits success. Why is that? I didn't give it an argument. This resolves to nothing, okay? If I give it a bad argument, if I give it hello, it returns immediately with success. Why does that happen? Because ping is given the -c argument of whatever resolves here. This is called arithmetic expression. I covered it in my bash course. If you want to go check it out, I'll have the link in my description. I'm not plugging a paid course. It's totally free. It's a video on YouTube. That's all I'm actually saying. But this is called arithmetic expression. It allows you to do math and bash. So I'll show you what that looks like on the command line. If we do 5 plus 5, you can put the spaces around it. You don't need the spaces. It's completely valid to just do it all like this and get really claustrophobic. If you do this, you get math expressions. That's really great. What if we say hello plus 0? Look at that. We get some sort of weird failure. We get a mistake. Something doesn't quite work how we expect it. So let's go ahead and actually save that to a variable. S equals hello, echo s plus 1. Look at that. Look at that. The variable, we can even do $s here. You can omit the dollar signs when you're in an arithmetic expression. If we do this, it turns into a 0. That's not great. Any random string gets turned into a 0 here, and then the 0 gets added to 1. So ping runs with a -c of 1. It succeeds immediately, and then we don't actually end up sleeping. So depending on how defensive you want this program to be, I'd be worried about that. Two things. We're relying on these external tools to generate error messages for us, and we're not validating the input they're giving us. I would do a little bit of that here. Maybe I wouldn't do the numeric validation. You totally could, but what I would do is I would do something like this. I would say duration equals $1, and now I could say something like if -z duration. This means if the string is not set or it's empty, we can do this, and we can say like echo the name of our program. We could say usage, the name of our program, and then number, like that. And then we could write that to standard error, and then we can exit with 1, which is an error status code. So if we run this safe sleep now without an argument, you can see that we get a usage message. How nice is that? We get that, and the command fails. So that's pretty good. Now also you could check if it is a number here. I'm not going to bother doing that, and I'm going to kind of explain why, because I want to show something else that could potentially go wrong here, okay? Because let's bring back this sleep command, right? We're going to execute the sleep that exists on the user system. So let's go ahead and run safe sleep, and we'll get an error because we haven't given an argument. That's really good. Let's go ahead and give it a number of 1. It'll sleep for 1 second, right? That makes sense. Let's give it a number 2. Now it sleeps for 2 seconds. Hey, that makes sense. Let's give it 2.5. What's going to happen? Well, that's really cool. It slept for 2.5 seconds, right? Let's go ahead and prove it here just to make sure. But we can see that it slept for 2.5 seconds. That's really, really nice that the binary of sleep on my machine supports fractional sleep, but it doesn't have to. And what I mean by that is if we go over here, this is the POSIX specification for the sleep command. The sleep utility shall suspend execution for at least the integral number of seconds specified by the time operand. So at least that amount, very well defined. Seconds though. It is in seconds resolution. So the fact that my system has a binary that supports fractional sleep is really great. Your system technically doesn't need to have that. So be careful with this. I don't know how they're running this tool. If they're only ever using integer sleeps, hey, that's great. You don't have to worry about this. But be careful because some of these won't work with fractional sleeps. Like look at the ping example. What do you mean I'm going to do 5.5 plus 1? Well, in Bash, we're just going to round that down. That's what's going to happen there. We don't have floating point numbers. So be mindful of that. If that's something you want, some versions may support it, some versions may not. Just be careful with that. That's something to consider here. Now we can go through, we can do a little bit of cleanup here. So everywhere we have $1, where we have it defined, look, it's in the code a bunch of places. We can go ahead and replace that with, what is it, duration? Yeah, there we go. And the nice thing is we don't need the dollar there. We can just use duration here in the arithmetic expression, and then we'll just swap it out here. So duration, 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 and then duration. There you go. So this will work exactly the same. We just swapped it out for the word duration, and this should work because we're just using the argument. We've gotten the argument from the user. We don't need to use $1 here. This would allow us to do any sort of modifications. Maybe we want to do some sort of floor division on it, get rid of the decimal point if there is one. Again, I don't know what this is meant to be used for, so I'm not going to bother with that. Here's the interesting thing. Because we're checking if we're in Bash, I don't know what this is meant to run in. If I were writing the script, I'd be using double square bracket notation everywhere. It's a bashism. I have a bash shebang. I'm assuming this is a Bash script. I would use that everywhere. But if we're not making that inference, if we're not sure that we're in Bash, then don't use that. However, it is used down here in the fallback method. So, I mean, I really don't know who's to say. So I'm going to clean this up exactly how I would clean it up. So I would be using the double square bracket notation everywhere. I would quote this expansion here. It doesn't matter. It doesn't technically need to be quoted, but I like to just quote all my expansions when they're being executed like this because of potential word splitting issues. This -n Bash version, maybe I would keep it. Again, if I'm writing a Bash script, I would just get rid of it. So you know what? I'm rewriting this for my system. I'm going to get rid of it. So we take this and we re-tab the whole file. It's going to make a lot of people upset because I like to use my hard tabs and get rid of the 4 spaces. This is just my style. Now, again, same thing here. This could be rewritten because we've already given a comment saying we're using standard in, standard out, and standard error. We could do something like this. We could do for FD in 0 to 2. I would actually just write it 0, 1, 2. I think that's easier to read for this example because we're not actually doing a range. We're using 3 very well-defined numbers, 0, 1, and 2, standard in, standard out, and standard error. Because they're so well-defined, I wouldn't use the range operator. I would do this. And then we could just put one of these in the loop, get rid of 2 of these. And then we have this, use our double square bracket notation here. So we could say, what's the name of this variable? Let me get that bracket right. What am I doing wrong? There we go. Look at that. I can code. I swear I'm good at this. So if the read command is available, then we'll loop over the FDs. If there is a TTY at that FD, then we will go ahead and read from that for that duration. Let's go ahead and give the FD there. And then we'll exit 0, assuming the sleep was successful. And if all of that fails, then we go down to our busy wait down here. So this will work for a lot of systems. Not all systems. There's a couple more things we can do. I'm going to talk about one more thing we could add and one way that this could potentially break on a system. So first things first, your version of Bash may have some loadable plugins. These are plugins that may or may not ship with your version of Bash, but can be loaded at runtime. I talk about these in a previous video where I made a web server using nothing but Bash built-ins. That is real. I'm not lying. It is a full-fledged HTTP server using Bash built-ins. I only had to cheat a little bit by using a loadable plugin that is in the Bash source code. It's shipped with Bash, but I have to load it in at runtime to listen on a socket. But we can do the same thing here. Bash may or may not have a sleep built in. So if I look at this, if I run type on sleep, you can see that it is an external command. It exists on my system. It's been sleep, but I may have it on my system. I can do enable sleep. And look at this. That worked. Type -a sleep. Now it's a shell built in. It's built into Bash, but it's a loadable plugin. It has to be loaded in a runtime. So again, your version of Bash may or may not have it. Now we can run help on sleep, not man. Man pulls up the commands manual page. This pulls up the help page, which is built into Bash. Now we can see suspend execution for a specified period. Sleep suspends execution for a minimum of seconds dot fraction. It also accepts the GNU style time intervals. So look at this. We now have fractional sleep, and we also have this new possible vector for allowing things that kind of look like strings. So you got to weigh your options here. If you want that fractional sleep, that's awesome, but you also widen the domain of acceptable inputs that may not be acceptable to you personally. Again, this is your project. You got to figure out what makes sense for you. So if you wanted to, if you know you're only getting integers from the person, maybe you validated the integers somewhere, you could do this. You could say enable sleep. And then you could like throw out errors if you didn't care. So I could do this. I could say enable sleep. Either this works or it doesn't. That's as simple as that. Either it works or it doesn't. If it worked, then we're going to use the built-in sleep. If it didn't, we're going to go out to the system sleep. You could do something like that. You could really enforce this. You could say, or, exit 1, like we have to have the built-in sleep. I wouldn't write code like this, but you could totally do something like this if you wanted to. I'm going to leave it out. I just want to show that as an example. And I also want to show some way that this could break, because we're using a weird mixture of like POSIX and Bashisms here, but then we're making a really, really wild assumption about ping, because ping doesn't have to really operate this way. Let me show you what I mean. Because if I go here, I am on my Mac. If I ping -c5 localhost and I run it, localhost is just 127.0.0.1, which is the same thing. You can see that it goes for 5 times. And if I were to time this, it should take 5 minus 1 seconds. It should take 4 seconds. So let it run. And look at that, it takes 4 seconds. Now ping works this way on a lot of machines, but not all machines. So look at this, I have another POSIX machine here. It has its roots in Unix. This is Illumos. So we are running on Illumos over here. This is OmniOS, and you can see like SunOS shows up. If I run this, we can get some information about the machine, so we can see like specifically what we're running, but this is on the Illumos kernel. So why am I showing this? Because let's go ahead and ping something and see what happens. So let me go ahead and ping localhost. Okay, well that just returned immediately. What if we gave it the arguments that the script was giving? Let's ping -c5 localhost. Uh-oh, that returned immediately. That was very quick. Ping on Illumos just pings the system. Sends it one packet, one ICMP packet, waits for one ICMP reply, and it checks if it's alive or dead. I remember the first time I encountered this back in 2010. I'm like, that's crazy. Why doesn't it just run forever? And then I really thought about it, and I was like, wait, why do so many operating systems just run forever when I run ping? Like, why isn't that hidden behind a flag? Why wouldn't I just ping it once? So I shifted my mindset a little bit. So yeah, if you're seeing this for the first time and you're like, why does it work this way? Why do the other pings work the way they work? You ever go on Windows? I think Windows ping works, 4 times by default, and you have to specify it to keep going? It's weird. It's a weird world out there. So ping is not going to be the same across all your systems, but you can get the same behavior. I just have to give it -s. So -s tells it to kind of operate like how the other ping things that you're used to work, and ping will just run forever because I gave it -s. I gave it -c5, but what does -c even do? Because remember, we're not on my Mac, we're not on Linux. What's happening over here? We can go down here, we can look at, where is it? Let's search for -c. -c takes a traffic class. The value must be an integer in the range over here. Gateways along the path can route the probe packet differently depending on the value of the traffic class. Dude, I don't know. Like, I have no idea what that is. It's embarrassing how little networking I know. But my point is the -c does not work the way you expect it to work over here. So you'd have to look for something like times or max times. I don't actually know. I'm going to be totally honest. I don't even know if there's like a count or any sort of amount that this can run. There might actually not be. I really don't know. Oh, wait, hold on. Was that n packets at the end of it? Data size and n packets. How does that work? The default data size is 56 bytes, or you can specify a size with the data size command line argument. If you specify the optional n packets. Okay. So I guess we could just do that. Ping localhost. So this is so interesting. I can run ping -s localhost, and then I can do like 56 as the size, and I can do 4 here. All right, well, today I learned. I actually didn't know that was possible. That's super cool. So I can specify like 2 here, and then we can run it 2. And if I don't give it a size, okay, so it assumes it's the size of 2. Huh, that's so funny. Oh yeah, look, 64 bytes received and 10 bytes received. That's so funny. That's interesting. This is genuinely today I learned because I just never needed this functionality. I think it also said it takes an I, which is the interval between, so it does 1 second between. I could probably do 3 over here. So now it'll wait 3 seconds between each packet it sends. That's very interesting. That's cool. Wow. Cool. So today I learned. My point is, let's bring it all back home now. In this safe sleep script, if we fail the sleep check, we go down to this command -v ping, and as you can see, this ping just won't work on Illumos. Now again, this isn't my project. I don't think that was meant to work on Illumos. I have no idea if it is or not. When I go over to the projects page, I can see that they have prereqs for what looks like Windows, Mac, and Linux. So I'm assuming Illumos is just not one of these things. That's fine. It doesn't have to work for this. My point is, it's a weird mixture in this script of like POSIX style and then suddenly just some utility that may work how you expect it to sometimes. So yeah, that's kind of my that's my deep dive into it. This is like what my final script would look something like, but I'd have to really understand why this was necessary, what we're trying to accomplish, what problems were there. It's probably all there in the issues. I'm sure there's a rich history behind it. Like I said, I'm not diving into that. I'm not relitigating this. This is not my project. I'm not part of that community that works on it. I'm not part of the core dev team, so it's not my place to say anything. I can just make some changes here and show you guys the cool bash stuff behind it. Also, if you are looking at this and you think, oh, Dave, you should make a pull request, or I'll take your code and make a pull request, do not do that. Do not do that. We don't need to do that. And the reason I say that is because with this project specifically, take a look at this. You go down here, this is the repo, this is the main README of the repo. Thank you for your interest in the GitHub repo. However, right now we are not taking contributions. So that is why I'm not going to take this script. I wouldn't do this anyways because there's so many things specific to my system. I'm not going to go here and make a pull request. I'm not going to bring this back up. I'm not going to say, hey guys, I fixed your script that wasn't even that broken because of some theoretical situation I imagine. That's not helpful. That's not helpful to anyone. It just wastes people's time. I don't want to dissuade you from being useful and making good contributions to open source projects, but as someone who's received pull requests, I do hate the drive-by pull requests because when you make changes, you're kind of putting load on other people. You're putting cognitive load over there saying, hey, I made some changes. Now bear the burden of this forever. It can be useful. Don't get me wrong. Like I said, I don't want to dissuade you from making changes, but if you're thinking, Dave, you should make a pull request here. No. They specifically say this right here. If they watch my video, someone there and wants to incorporate some of this, feel free, use it. I don't care. You can take whatever you want from here. I don't mind at all. But my point is, like, they specifically asked this, so don't go over there and be like, I'm going to make some changes that no one asked for. Don't do it. Don't do it. It says right here. This video is just meant to be educational and provide entertainment. Okay. So I hope you guys enjoyed that. That's sort of my deep dive into this. So here's kind of what the final script looks like. And now we have our own version of safe sleep. Again, if I were writing a script, I would just use the sleep binary. I don't know what their specific situation is. I don't know why they needed this. I'm sure there's some reason, but here we are. So if you made it this far, you're awesome. I want to give a shout out to my Patreon members over at Patreon. Check it out. You want your name at the end of one of my videos? Go sign up for my Patreon. There you go. It's awesome. And of course, I just released my bash course. Go check it out. You can go there in your browser, or you can do it on the terminal. Look at this, course.ysap.sh, course for bash course. YSAP is You Suck at Programming, my website, .sh, because it's a cute little bash thing, little shell thing. Look at that, 7+ hours, 60+ sections, created by me And here's a link to it. It's free. It's on YouTube. I'm not charging you anything for it. 7 hours of content. Really good content. I promise you. It's amazing. I'm so good at what I do. I'm just kidding. But yeah, go check it out. Thank you for watching, everyone. Have a good one. See ya.